Hello friends, in this lecture we will continue to look at quantization. We have seen that quantization is the process of discretizing the amplitude of an analog signal. Quantization essentially is a many-to-one mapping which leads to some error known as quantization error. So in this lecture we will look at quantization error and the 6 dB rule of PCM. So what is quantization error? So let us recall that quantization is a many-to-one mapping. Mathematically, V equal to G of M, where M is the sample value, G is the quantization function, which maps this sample value which belongs to a continuous set to a value which belongs to a discrete set. For example, suppose our quantization interval is 0 to delta. So whatever value that falls within this interval 0 to delta is mapped to one quantization level delta by 2. So how do we quantify this error? So the quantization error, we denote it by Q, is equal to V, the quantized level, minus M, the actual sample value. Looking at this expression, the maximum error that we get here, Q equal to, when M is equal to 0, then the maximum error is delta by 2 minus 0, and that is delta by 2. So when M is equal to 0. When M is equal to delta, the error will be delta by 2 minus delta, V minus M. So the error will be minus delta by 2 when M is equal to delta. So we see that the maximum quantization error in uniform quantization that we have been discussing is delta by 2 or minus delta by 2. And because the length of quantization intervals are all same, the step size is fixed delta, the quantization error, the random variable Q in general can be written as capital V minus capital M using the random variable notation. So the quantization error Q has a uniform distribution in the interval minus delta by 2 to plus delta by 2. And therefore, let me just write here, this small q denotes an instant, a particular value, and capital Q denotes the corresponding random variable. So this is the random variable describing the quantization error. So this quantization error is a uniform random variable and can be depicted like this in the interval from minus delta by 2 to delta by 2. It has a PDF FQQ. The PDF is a rectangular function and the height of this rectangle must be 1 over delta because the area under any PDF curve must always be 1. Okay. So FQQ is equal to 1 over delta for small q lying in the interval minus delta by 2 to plus delta by 2, and it is 0 otherwise. Let us compute the mean value of this quantization error. So EQ by definition is integral minus infinity to infinity Q FQQ dq, which here we can write as integration minus delta by 2 to delta by 2 because FQQ is 0 outside this interval. Q times FQQ is 1 by delta in this interval. So 1 by delta dq, and that is equal to 1 over delta into q square by 2 limits minus delta by 2 to delta by 2, which is clearly 0. So the mean value of the quantization error is 0. Let us compute the mean square value. EQ square, which is equal to, by definition, minus infinity to infinity small q square FQQ dq, substituting the values. So basically this will be, when we put the value of FQQ, The interval is minus delta by 2 to delta by 2. So minus delta by 2 to delta by 2 q square into 1 by delta dq, and that is equal to 1 by delta. When we integrate q square dq is q cube by 3, limits minus delta by 2 to plus delta by 2, and that is equal to 1 over delta, and you'll get here delta cube by 8 minus delta cube by 8. So basically delta cube by 4, and then 3 is there, 1 delta will cancel, and what you get is delta square by 12. Okay, so this is a very important result. It says that the mean square value of the quantization error is equal to delta square by 12, and mean square value denotes the power. So we can say that what it denotes is the quantization noise power. What about the variance? The variance of Q, which we denote as sigma Q square, is equal to the mean square value minus mean value squared. And because the mean value is 0, so mean square value is delta square by 12 minus mean value is 0. So it is equal to delta square by 12. So in this case, the variance of the quantization noise is same as the mean square value, and therefore it also denotes the quantization noise power. So here the variance is same as the mean square value, and hence the quantization noise power. Writing once again, sigma q square is equal to delta square by 12. But delta, the step size, is the dynamic range upon the number of quantization levels, as we have seen already. 2m max by L, the number of quantization level, so that is delta. So delta is squared by 12, and thus we get here m max square by 3L square. Now, if we use 1 bit to represent a quantization level, there will be 2 quantization levels. If we use 2 bits, then there will be 4 quantization levels. In general, if we use R bits to denote a quantization level, then this implies that there will be 2 to the power R quantization levels. That is L equal to 2 to the power R. So these many quantization levels will be there. So substituting 2 to the power R for L in this expression, we get sigma q square equal to m max square upon 3 into, in place of L we write 2 to the power R square, or m max square upon 3 into 2 to the power 2R. Now usually this quantization noise power is expressed in decibels, and therefore in decibel scale sigma q square in dB will be 10 log to the base 10 of this quantity sigma q square, that is m max square upon 3 into 2 to the power 2R, and that becomes sigma q square in dB equal to 10 log m max square minus 10 log 3 minus 10 log 2 to the power 2R to the power 2R, or we can simplify it further. It becomes 20 log m max minus 10 log 3 minus 20R log 2 to the base 10. Now, this log 2 to the base 10 is approximately equal to 0.3. So 0.3 into 20 is 6. So we can further write sigma q square in dB equal to 20 log to the base 10 of m max minus 10 log 3 to the base 10 minus 6 times r. This is a very important result which says that for every single bit increase in representing a quantization level, the quantization noise power reduces by 6 dB, and therefore equivalently the signal to quantization noise power ratio increases by 6 dB, and this is known as the 6 dB rule of PCM. The exact value of this expression will depend on what kind of signal we are dealing with and what is the maximum amplitude of that signal, M max. But the rule remains true in general. So this expression implies that for each additional bit, the quantization noise power decreases by 6 dB, and therefore the signal to quantization noise ratio increases by 6 dB, and this is known as the 6 dB rule of PCM. So what is PCM? PCM stands for pulse code modulation. It is a waveform coding process by means of which an analog signal is represented by a sequence of coded pulses. So what we have seen so far is that we have a source of information, and that information may be and usually is in the analog form, and which must be digitized for further processing. The first thing that we do is we use a low pass filter that acts as an anti-aliasing filter to band limit the signal so that the sampling can be done without the risk of aliasing. So sampling discretizes the signal in time, and then quantization discretizes it in amplitude. And here we get a digital signal. This quantization may be uniform or non-uniform, as we will see afterwards. And then once we have digitized our signal, it must be represented in the form of a sequence of coded pulses, and that process is known as pulse code modulation. So sampling, quantization, and encoding, these three together form PCM. Once we have obtained a coded representation, the pulses are transmitted through the channel, maybe directly as in baseband communication, or after modulating a carrier known as passband communication. And then at the receiving end, the reverse process takes place to recover the message signal. So that's all for this lecture. Thank you.